Okay, in the last class we are discussing about various peripheral devices such as 8255 programmable peripheral interface, 8254 programmable interval timer, 8259 programmable interrupt controller. The next peripheral device is programmable DMA controller. Programmable DMA controller. So, before going for this programmable DMA controller, I will discuss first what is the necessity of DMA controller. So, we know that the data transfer between the memory and peripheral will take place through the microprocessor. If you take the microcomputer block diagram, this is the microprocessor, then we have the memory, then we have I/O. We have bidirectional signals from memory to I/O and I/O to microprocessor. So, the normal way of data transfer will be, so if you want to transfer the data from I/O to memory or memory to I/O, say so for example I/O to memory. So, I/O will write onto the microprocessor, then microprocessor to memory. This is the conventional way of data transfer. But the drawback of this conventional data transfer scheme is, if I use this I/O device such as a fast device, if I/O device is, if I use the disk, floppy disk or hard disk, or it can be an optical disk such as DVD, CD, the rate of data transfer from the I/O is very fast. In such cases, the data rate is very fast. So, the data rate is fast. So, normally in case of conventional data transfer, how this data will be transferred from I/O to memory is through the program instructions. So, in this conventional data transfer, the data transfer takes place through program instructions. That is software. This software type of data transfer. So, the drawback of this type of program instructions or software type of data transfer is, so in order to fetch the instructions and to execute the instruction, it will take some time. So, the time that is taken to fetch the instructions and execute the instructions is less than that of the data rates of the hard disk or optical disk. So, as a result of that, it becomes difficult to transfer the data from I/O to memory through microprocessor using software instructions. So, in order to avoid this problem, so we need a hardware element, dedicated hardware element which is faster than the program instructions, which can enable the data transfer between the I/O to memory directly. So, for that we require a direct memory access controller. DMA controller. So, this is a hardware device. Unlike in case of conventional data transfer, where the data transfer takes place through software instructions, the drawback is execution of this instruction will take more time, and the data rate of I/O devices is large in case of hard disk and optical disk. So, it becomes difficult to transfer. Now, using this DMA controller, what we will do is, so we will transfer the data from I/O to memory through DMA controller. This type of data transfer is called direct memory access data transfer. Direct memory access DMA data transfer. It is obvious that because this is a hardware device, so this is faster than the software type of data transfer. This is the advantage of DMA controller and need of the DMA controller. Now, if I draw this diagram in a somewhat detailed manner, so that we can understand what is the step by step procedure that will take place to transfer the data from IO to memory directly without involving the microprocessor. There is some step by step procedure is there. So, if you consider this detailed diagram of DMA controller, this will be something like this. There is a microprocessor. So, this can be any microprocessor. Here I will consider 8086. Then we have memory. The same previous diagram I am going to show in detail. We have memory, and then we have peripheral, then we need a DMA controller. Direct memory access controller. The connection details are, the 8086 will be having address bus, data bus and control bus. So, in order to transfer the data from peripheral to the memory or memory to peripheral, the DMA controller must contain this address, data and control bus, but these are with 8086. Okay. For that we need a switch type of configuration. So, through this switch configuration we can transfer the control of this address, data and control bus to the DMA controller whenever needed. Okay. So, we will be having address bus. So, only we are assuming that only 16-bit address is enough. So, we will take A15 to A0, but this is multiplexed. In case of 8086 we know that address bus and data bus are multiplexed. This actually in fact will be available as AD15 to AD0. This is AD15 to AD0. This is 16 lines. In order to demultiplex this address and data bus, we require a signal called address latch enable, ALE, and this is latch. So, the output address will be latched. Here this will be address bus, which contains A15 to A0. In the first cycle we will latch the address. So, in the subsequent cycles we will use the same bus to carry the data. Now, this will act as data bus, D15 to D0. Then this will be having some control bus. This is control bus. The signals that are contained in control bus are memory read. As I have discussed in the very first class of this course, the microprocessor can perform 4 operations: memory read, memory write, IO read, IO write. All these signals are normally active low signals, because AND gate is a universal gate. Then this memory also will be having address bus, data bus and control bus. So, we are going to connect this memory address bus to one of these switches. So, this is coming from DMA controller. So, we have address bus of DMA controller, data bus of DMA controller and control bus of DMA controller. So, this to be connected through switches to memory. This will be connected to memory through switches. There will be a switch now here, there will be switch here, there will be switch here. This is up position, this is down position. So, this is control bus of DMA controller, this is address bus of DMA controller, this is data bus. Then this data and control bus will be connected to peripheral also. Then between the DMA controller and 8086 there will be two signals. So, one is called hold request signal HREQ, HLDA signal. This will be connected to hold signal of 8086. We know that in minimum mode there is a hold signal for 8086 and this will be connected to HLDA, hold acknowledge. These two are minimum mode signals. And between this peripheral and DMA controller there is a DMA request signal and then DMA acknowledge signal. This is called DMA acknowledge signal and this is DMA request signal. So, you see the complete diagram of the DMA controller with 8086 memory and peripheral. Okay. Now, what is the step by step procedure that need to be performed to transfer the data directly from peripheral such as hard disk to memory. So, I want to directly transfer the data from peripheral to memory, but this will happen through DMA controller. Okay. So, if you come in for this step by step procedure, step 1, when the system is initially on, the 3 switches will be connected to the up position. So, what does it mean? The address data bus and control bus will be connected between the memory and microprocessor. It is clear from the diagram that. So, initially whenever the system is on, there will be a physical connection between the microprocessor and memory, and DMA controller will be bypassed. Okay. So, whenever you want to transfer the data from peripheral to memory, so the next step is when first data byte in peripheral such as hard disk is ready, to transfer to memory. So, the DMA controller, I will call DMA controller as DMA-C, sends, we can see that there is a connection between DMA controller and peripheral. There are two signals. The first signal is DMA request signal, sends a DMA request signal, DRQ on one of the channels of on one of the channels of DMA controller. So, DMA controller can have any number of the channels. So, later we are going to discuss a specific DMA controller 8237 that contains 4 channels. So, this DMA, the peripheral can place the request on any one of the channels. The next step is step 3. If the DMA channel of DMA controller, if the channel of DMA controller is unmasked, DMA controller is unmasked. If it is masked, then that service will not be recognized. If the channel on which the peripheral device has placed the request, if that channel is unmasked, then in response to this DMA request, because to transfer the data, the DMA controller needs address bus, data bus and then control bus. But now initially when the system is on, the switch is connected to the up position. As a result of that, the address bus, data bus and control bus will be connected between the memory and microprocessor. Now in case of DMA, we need to connect the address bus, data bus and control bus between DMA controller and memory. Okay. So for that, the DMA controller needs the use of the system bus, which is address bus, data bus and control bus. So it will request for the system bus through hold signal. If a DMA corresponding channel is unmasked, the DMA controller sends a request for the system bus. System bus consists of all the 3 buses, address bus, data bus and control bus, through hold request signal, HRQ signal. You can see this signal in the block diagram that I have drawn. This HRQ signal is connected to hold signal of 8086. So once this microprocessor receives hold request signal from DMA controller, then the microprocessor floats the buses in response to the hold request signal from DMA controller. In response to hold request signal from DMA controller, the microprocessor floats the buses, address, data and control buses and sends the hold acknowledge signal to DMA controller. So once the DMA controller receives hold acknowledge from microprocessor, the DMA controller sends a control signal to the switches. So then the switches will be thrown to the lower down position. The next step is the DMA controller sends a control signal which throws the switches to the down position. So it is clear from the diagram that when the switches come to the down position, there will be a physical connection between the memory to DMA controller. No longer this microprocessor will be available. Now, the connection for the microprocessor will be bypassed. Now, once the DMA controller takes the control of the system bus, address bus, data bus and the control bus, then it is ready to transfer the data between the peripheral and memory. Okay. Then the DMA controller sends the starting address of memory and the number of bytes to be transferred. To DMA peripheral. And sends acknowledge signal, say DMA acknowledge signal, DMA ACK signal to peripheral. Now, I want to transfer the data between this peripheral and memory. This is peripheral and this is memory. So, in the memory we have lot of locations, from which location onwards we have to transfer the data. This address will be sent by the DMA controller and how many bytes of the data you want to transfer totally. So, these two are the important factors. Okay, these two will be sent by this DMA controller through this DMA acknowledgement signal. It will tell this DMA peripheral device to be on for the first byte of data transfer. Okay. So, once this peripheral receives a DMA acknowledgement signal, then the peripheral places transfers the data to memory after the data transfer is over. Is complete, then the DMA controller sends a signal, control signal, which throws switches to the up position. So, again the microprocessor regains the control of the system bus, address bus, data bus and control bus. This is how the exact the DMA data transfer will take place. This is the step by step procedure. Okay. So, initially the first step is, so the system, whenever the system is on, there will be physical connection between the memory and microprocessor. That time DMA control will be bypassed. Okay. So, whenever the first data byte in peripheral is ready, so this peripheral will first request the DMA controller through this DMA request. Then in response to that, the DMA controller, because this requires the control bus, data bus and address bus, it will request the microprocessor through hold request. So, in response to that, the microprocessor will respond through the hold acknowledge, and then it will tri states, or it will floats in the sense tri states. So, we know what is meant by tri state, we have discussed it in the earlier classes. The control of the address bus, data bus and control bus to the DMA controller. Then the DMA controller will send a control signal to through the switches from up position to down position. Now, a physical connection will be established between the DMA controller and memory. Then this DMA controller will places, so which memory location onwards we have to transfer the data from peripheral to memory, or how many number of bytes to be transferred. This data will be placed and it will be sent to the DMA controller. Now DMA controller will transfer the bytes. Once the data transfer is over, again the switches will be thrown to the up position, so that again the physical connection between the memory and microprocessor will take place. This is the step by step procedure that will take place to transfer the data between the peripheral to IO directly without involving the microprocessor. Now here the data transfer will take place through the DMA controller, which is a hardware device. Because of that, the rate of data transfer will be fast when compared with the software data transfer, which takes place through the microprocessor. This is about the DMA controller. In the similar way, if you want to transfer the data from the memory to IO also, the same process will repeats. The only difference between this peripheral to memory or memory to peripheral, that depends upon the 4 signals. So in case of peripheral to memory, so you are reading the data from the peripheral, which is IO, you are writing onto the memory IO. This DMA controller sends 2 signals. We know that totally we have 4 signals, control signals, which is memory read, memory write, IO read, IO write. So in peripheral to memory, memory write will be enabled and IO read will be enabled. Because we are reading from the peripheral, which is IO, so IO read is 0, we are writing onto the memory, memory write will be 0. Whereas in case of memory to peripheral, other 2 signals will be low. Memory read will be 0 and IO write will be active low. Except for this, there is no difference between the data transfer between the memory and peripherals. So with this discussion, now we will go to the dedicated DMA transfer controller, which is called 8237 or 8237A. So 8237 or 8237A, there are some slight advanced version. So this is a dedicated DMA controller. So the discussion that I have made in the earlier slide is a general DMA controller. Now we will come to the specific DMA controller. So the features of 8237 or 8237A is, this is a 40-pin IC with 4 channels. As I have told in the previous procedure, so this peripheral device will place the request on one of the channels. Okay. The number of channels in a DMA controller varies from the device to device. In case of 8237, there are 4 channels, and each channel is capable of transferring 64 kilobytes of the data. So this is the one feature of 8237, and another feature is 8237 or any DMA controller in fact 8237 can operate in 2 roles. So one is IO device for microprocessor, and another one is it can also use as a data transfer processor. Data transfer processor. Between peripheral and memory. So, when the switch positions are up, it will act as just simply IO device, okay. Whereas in case of DMA, it will act as a processor, because the processor is no more available, microprocessor will be bypassed in case of a DMA data transfer. So, DMA controller itself will act as a DMA processor. This mode is called slave mode, because here the master is microprocessor. So, in the second role, this DMA controller will act as a master. This is called master mode. So, this DMA controller can operate in two roles. One as a slave in case of IO data transfer. In case of DMA data transfer, this will act as a data transfer processor. Then, because this 8237 is a complicated device, for a clarity I am going to divide this discussion on 8237 into 5 parts. The discussion on 8237 I am going to divide into 5 different parts for clarity. Otherwise, actually this is a complex device, so it becomes difficult to follow this. Okay. So, the first I will discuss about DMA interfacing. Then I will discuss about DMA signals. Then I will discuss about system interfacing, how to connect in a system. Then I will discuss about the programming and then execution. So, I will divide the entire discussion into these 5 parts: DMA interfacing, DMA signals, system interfacing, programming and execution. Coming for the DMA interfacing. So, if I take the DMA device 8237 or 8237A, this is 8237. So, total 40 pins are available. So, one is chip select signal. For any chip we require a chip select signal. Then we have the other side, this side is actually we will connect to the peripherals. This side will connect to microprocessor. As I have told, there are 4 channels, each channel will be having one DMA request, one DMA acknowledge. So, these are 4 DMA requests from the peripheral, as I have discussed in the earlier step by step procedure. So, DMA request DRQ, this is available as active high signal only, 0, DRQ1, DRQ2, DRQ3. Similarly, acknowledgement signals 4, DACK0, DACK1, DACK2, DACK3. Then we have one signal which is called end of process signal. I will discuss what is the function of this one, EOP. This is also active low signal, bidirectional signal. Coming for the other side, so we have 4 signals which are going to control 16 register inside the 8237. These are bidirectional signals. Or this unidirectional. This is A0, A1, A2, A3. Then we have a 3 to 8 decoder, 74LS 138. This I have discussed in the memory interfacing also. This is a 3 to 8 decoder, 3 inputs, then 8 outputs, O0 bar, active low signals all. This is O0, this is output 0 signal. So, this I will connect to chip select signal. Accordingly, you will get some addresses. If you want, you can connect O1, O2 also, O7 also. This will be having total O7. So, this is A0, A1, A2. Then we have 2 active low signals E0, E1 active low signals, and E2 there is active high signal. These are the different signals for a 3 to 8 decoder 74LS 138. So, this I am going to connect to this A0 to A4 is there. I will connect here A4, A5, A6, then I will connect this to A7, this I will ground, this is active high signal. So, I will connect this to M by IO bar through inverter. Okay. So, for IO this will be 0. So, I will connect a inverter here, this is M by IO bar, this signal is M by IO bar. In case of 8085 this is IO by M bar, we can connect directly. So, these are different signals. Then the remaining signals are, we have a data bus, total this A4 to A7 will be another A4 to A7, this actually in fact are connected here. Okay. And then we have data bus DB7 to DB0, data bus. Then we have 4 control signals we know, memory read, memory write, IO read, IO write. This is memory read bar, memory write bar, IO read bar, IO write bar. Similarly, we have the other signals, ready signal, reset signal, then you have clock signal, then as we have discussed in this step by step procedure, there will be a hold request signal HRQ and hold acknowledge signal HLDA. And there is one more signal called terminal count TC. So, these are the different signals available, because these are bidirectional signals. So, these are the different signals available on 8237. So, total we have 40 pins. So, this side will be connected to microprocessor, this side will be connected to the peripheral devices. Now, how to generate the addresses of the different registers present in the 8237 and how to connect this to the microprocessor. Okay. So, in order to connect to the microprocessor, it requires 2 more signals called address enable signal and address stop signal. Address stop is TB and address enable signal AEN. These are the different signals available. So, if I connect to the microprocessor, so I will show that connection of the microprocessor to 8237 in the next slide. So, coming for this the internal registers, totally we have 16 registers inside the 8237. So, the register of 8237. Correspond to each channel we have two registers, one is called memory address register, another is called count register. This is memory address register correspond to channel 0, memory address register, I will call as MAR, correspond to channel 0, and correspond to this same channel 0 we have count register. So, MAR of channel 1, and count register of channel 1, MAR of channel 2, total we have 4 channels. And count register of channel 2, MAR of channel 3, count register of channel 3, so total 8 locations. So, I will generate the addresses by using the interfacing circuitry. So, I will write here the corresponding address. So, we know what is the purpose of this memory address register. If you want to transfer the data from peripheral to memory, peripheral such as hard disk, peripheral to memory, how many bytes of data has to be transferred, and what is the starting address of the address. So, the starting address of this location where the first data has to be sent, we have to place in memory address register, and the number of bytes to be transferred we have to place in count register. Okay. So, the remaining 8 locations of this 8 registers of 8237 are, this is read write, signal, status / command signal, command register, then you have write request register, write single marks register, write single mask, register, write mode register, we are going to define the various formats of these registers. Write clear byte register, flip flop, we have read write master clear, / temporary register, so total we have 1 2 3 4, here up to here is 8 9 10 11 12 13 14, we have 2 more registers. So, write clear mask register, write all mask register. So, these are the different 16-bit registers, all are 16-bit registers. Then how to know these addresses of these registers? That will be decided by the previous decoding circuitry. Here, in order to select this chip, chip select should be 0. If it is, if I write this A7 to A0, A7, A6, A5, A4, A3, A2, A1 and A0. So, in order to select this chip, the output of O0 should be 0. So, that these 3 should be 0, 0, 0, then only the first output will be selected. So, A4, A5, A6 should be 0, 0, 0, A4, A5, A6, and this A7 should be 0 because this is connected to E0 which is active low signal. So, with these 4 zeros this chip will be selected. After that this A3 to A0 is going to select the channels. If this is 0, 0, 0, 0, the first address. So, the first address of this one will be this memory address register of channel 1. So, this address will be now 00H. So, this A7, A6, A5, A4, A3, A2, A1, A0. So, these 4 are 0, 0, 0, 0 to select the IC. This varies from 0, 0, 0, 0 to, so if it is 0, 0, 0, 0, 0, 0 H. This can be 0, 0, 0, 1, so that 0, 1 H, 0, 0, 1, 0, 0, 2 H, so on up to 1, 1, 1, 1 is FFH. Because this remains 0, 0, 0, 0 only for all the registers, because if they are not 0, 0, 0, 0, the IC controller itself will not be selected. So, the address of this one is 00 H, address of this one is 01 H and so on, 02, 03 up to 0 FH. This is 0 FH. Zero 4H, 05, 06H, 07H, 08H, 09H, 0AH, 0B, 0C, 0D, 0E, 0FH. This is how we can generate the addresses of all the registers. Now, this is the second step, as I have told for the clarity. I have divided this discussion on 8237 into 5 subgroups. So, this is the interfacing circuitry, and second one is system. So, DMA signals also we have already discussed. So, we have discussed all the functions of this DMA signals. Ready signal is, so whenever this 8237 is ready, so this will be one signal will be generated. Similarly, reset, clock, these are default signals, and these are this DMA request and DMA acknowledge signals. End of process. So, whenever this process is completed as by name it implies that if EOIP is 0 means process is over. So, these are the different signals. Then system interface. So, if I connect this come to this internal diagram of 8237. So, whatever I have drawn here in the earlier slide is only just a block diagram. Now, we have the complete details here. So, we have all the signals. So, this is a data bus buffer, so which will be having 8 data lines. This is read write logic. So, this chip select we have generated, then we have reset signal. The microprocessor can reset the 8237. This is clock signal. The clock can be given from the microprocessor or we can give from the clock generator also. This IO read, IO write are bidirectional signals, active low signals, because in IO we can have input operation as well as output operation. This A0, A1, A2, A3 will be used to generate the address of the registers just now have discussed. Then we have A4, A3, A5, A6, A7, these are used for generating the chip select signal. Then we have ready signal that will be controlled by the microprocessor. This side, as I have told, this side will be connected to microprocessor, this side will be connected to peripheral such as hard disk. And this is hold signal, hold acknowledge signal, which I have already discussed, memory read, memory write. This AEN and AD STB, these signals are used for latching the higher order 8 bits of the address. They are used to latch higher order 8 bits of the address. That is A15 to A8. Then terminal count. Once if you load the count into the count register, and you have to decide whether the memory locations has to be auto increment or auto decrement, that you can do using the mode control word or the command control word. Then once this count is 0, after each transfer the count becomes automatically decremented by 1. Once the count becomes 0, it will indicate through this terminal count signal. And here these are the 4 channels, channel 0, channel 1, channel 2, channel 3, each will be having one request signal, one acknowledge signal, and we can assign the priority to these signals. Okay, similar to this programmable interrupt controller, where we can assign this priority, here also we can assign the priority in 2 ways. One is called fixed priority, another is rotating priority. Fixed priority will fix the priority, whereas in case of rotating priority, we can follow some rule like the channel which recently served, we can assign the lowest priority. This also can be programmed using the mode word registers. This is the internal details of 8237. And coming for this the various control words which we are going to use to select the modes of DMA, we have different control words. So first one is a current address register, as I have told. So if you want to transfer the data from peripheral to such as hard disk to memory, so where does the first byte has to be transferred? What is the address of this one? So this will be decided by this current address register. This holds 16-bit memory address used for the DMA transfer, the starting address. So this each channel will be having its own address. This may be correspond to some channel is some 4000 is correspond to channel 0, and for channel 1 you can have some 5000. Channel 2 you can have 6000. As I have told, each channel is capable of transferring maximum of 64 kilobytes of the data. Channel 3 will be having some other address, say 7000H. This will be decided by current address register which is present inside the 8237, and this can be either auto increment or auto decrement, that will be decided by the control word registers that we are going to discuss in the coming slides. Then we have count register, as I have told. So if you know the starting address of the memory, then the next question arises is how many number of bytes you want to transfer, that will be stored in this count register. Just now I have told that each channel will be having 2 registers, one is called memory address register which stores the starting address of the memory, and current word count register which stores the number of bytes to be transferred. Then we have command register, so which will decide the operation of DMA controller. So, whether this is from peripheral to memory or memory to peripheral or even memory to memory operation also possible. Okay. So, I will see the format of this command word register in the next slide. So, this is the format of command word register. This we have to load into 8237 before you are going to transfer the data. Okay. This is self explanatory. So, the last bit represents, if this is 0, then memory to memory transfer will be disabled. If this is 1, memory to memory transfer will be enabled. This is self explanatory. Similarly, second bit can be 0 or 1, depends upon whether channel 0 address has to be hold or we have to disable. If this is 0, channel 0 address will be hold. If this is 1, channel 0 address will be enabled. The third bit will be DMA controller, whether we want to enable or disable the DMA controller. Now, the question is when you want to disable the DMA controller. So, depends upon the initialization, whether it is auto initialization or we are going to initialize by the programmer. So, if the programmer want to initialize, that time you have to disable this controller. Okay. This will be clear if I give an example. So, 0 means controller will be enabled, 1 means controller will be disabled. And the timing also, we want the normal timing or compressed timing. So, we can compress the time also by scaling factor, but normally we will use normal timing. So, for normal timing 0, for compressed timing 1. As I have just now told, this can be having fixed priority or rotating priority. So, this will be decided by this bit, and the next bit will be, next bit decides whether late write selection or extended write selection. So, if this is 0, late write selection, otherwise extended write selection. So, this depends upon the speeds of the devices. If it is late, you have to select the late write. Okay. This depends upon the specifications of the peripheral that we are going to connect. Then we have D request and D acknowledge can be either active high or active low. Okay. This is up to you. So, we can program the status or the level of DMA request and DMA acknowledge signals. So, this is the format of command register. So, I will write the program using this command register after some time. Then the mode register, there are two important registers, one is command register, another is mode register. So, mode register, as the name implies, it will select the mode of operation. So, this will decide the channel to be selected. So, if this is channel 0, 0, 0, channel 1, 0, 1, channel 2, 1, 0, channel 3, 1, 1. So, we can have the 3 operations. In addition to read, write, we can verify the data also. Suppose some data is present in the memory, I want to verify whether the same data is present or not. That operation also possible through DMA controller. So, for that we will use this as 0, 0 for 0, 1 write operation, 1, 0 read operation, whereas 1, 1 is illegal. And the next bit is auto initialization, enable or disable. As I have told, in case of auto initialization enable, we have to enable the DMA controller in the previous mode. If auto initialization is disabled, then I will disable the DMA bit in the previous this one. Here this controller will be enabled or disabled. This depends upon whether we are going to provide auto initialization or the mean initialization provided by the programmer. And the memory address, we are going to specify the starting address of the memory. So, whether the data need to be transferred in the ascending order or descending order, whether the memory address has to be incremented or decremented, that will be decided by this bit. 0 means address increment, 1 means address decrement. Then we have different types of the modes. So, demand mode select, on demand we can transfer only single byte, and we can transfer a block of bytes. And this is also possible to cascade 8237, similar to 8259, we can also cascade different 8237s to handle different peripheral devices. So, these two are the important registers which we have to use for programming. As I have told, the next step is programming. So, in that I have to use this mode register and command register, right. And there are some other registers which will be normally will not use. I will just have a quick click on the quick look. So, this is called bus request register. So, these signals are obvious from this slide. So, these are the channel selections, and this bit will be 1 if it sets request, 0 reset the request bit, and the remaining all are do not cares. This will be useful only in memory to memory transfer, but memory to memory transfer is not that important, because memory is the speed of the memory is almost compatible with the speed of the microprocessor. Where the DMA controller is important is in case of peripheral to memory, because peripheral is first device. And we have mask register, set, reset. These are all I have discussed in the 16 registers, the table that I have given. So, these are the formats. So, these are all self explanatory. This is mask register. So, we have 0 for clearing channel 0, 1 for enabling or setting the channel 0, similarly for channel 1, channel 2, channel 3, the remaining all are do not cares. This is the status register. So, after loading this starting address of the memory, and then the number of byte to be transferred. Okay. So, after each byte transfer, the count will be decremented by 1. Okay. So, whether this count becomes 0 or not, that status you can verify through this status register. So, if channel 0 reached the terminal count, TC stands for terminal count, then this bit will be 1, otherwise 0 means the data transfer is in progress. So, if this is 1, implies that the terminal count has been reached. So, the DMA controller can relinquish the control of address bus, data bus and control bus, the control of the 3 buses to the microprocessor. Similarly, this is for channel 1 terminal count, channel 2 terminal count, channel 3 terminal count. So, which channel has been requested? So, we can request the peripheral can be connected to channel 0, channel 1, channel 2 or channel 3. So, if want to request through channel 0, this bit we have to make as 1, channel 1 this bit we have to make 1. So, this is also possible that at a particular time more than one channel becomes 1. So, in that case you have to assign some priority. According to the priority you have to decide to whom this request has to be granted. So, these are the different registers. Now, coming for the programming, I will discuss on these registers itself, the command registers. Suppose these are the specifications of the program that I want to write. So, I want to transfer 1 kilobyte of the data, transfer 1 kilobyte of the data from memory to hard disk on channel 3, and the starting address of the memory should be say some 3455H. And I want to use auto normalization, auto initialization, disable, and I want to use normal timing, fixed priority, late write selection, and I want to use both D request. So, in fact this is DRQ or DREQ. In some books it is written as DRQ and in some books it is written DREQ. DRQ both are same only, okay. And D acknowledge, I want to use this as both are active high signals. So, these are my specifications. For that you have to write the program. So, the first step is we have to find out what is the command word register. So, what will be command word? So, what will be these bits? So, what about the last bit? It is not a memory to memory transfer. So, I have to disable the memory to memory transfer. So, this will be 0, and then coming for the next bit, this is channel 0 address hold disable because we are not using the channel 0. So, I want to disable this. Then because I want to disable auto initialization. So, this bit also will be controller we have to disable. So, this will be 1 because I want to disable the controller, then only I can initialize the process. Otherwise, if I enable this controller, it will do the automatic initialization of the process. Then I am using fixed priority. So, this will be 0, then late write, this will be 0. I want to make both high, D request high means this will be 0, D acknowledge high means this will be 1. So, this is correspond to 8. One more bit is, this is last one is 0, then last but one is 0, controller is disabled is 1. So, normal timing is 0, fixed priority is 0, late write is 0. Then we have one more bit here, this D request is, this is 0 for active high and this is 1 for active high, D acknowledge. So, what will be this one? 8 4H. So, what is the address of this command register? If I use this circuitry which I have used in the earlier slides. So, for this connections I will assume these connections. Okay. For these connections, what is the address of command register? So, in this where is the command register? This is the command register, the corresponding address is 08H. So, what are the instructions? So, the instructions are move AL, I am discussing the programming here itself, this is what is called programming. Move AL comma 84H, I have to place this into the command word register whose address is 80H. If I assume the interfacing connections that I have discussed in the earlier slide, then we have to write out 08H comma AL. These two instructions are used for setting this command word register. Then coming for the second register which is mode register. So, what will be this data of mode register? So, the last 2 bits, because I am using channel 3, these two are 1 1 and I want to use write operation, write into peripheral, because I want to transfer from memory to peripheral. So, this is 0 1. Then I want to disable auto initialization 0 and I want to increment the address. So, this is also another specification, we can write in the previous the specifications, increment the address. So, 1 byte of the memory starting from this address to, so what is the ending address? If I want to increment this, 1 kilobyte is equivalent to 1 kilobyte is equivalent to 03FFH in hexadecimal. So, ending address will be now 3455H plus 03FFH 03FFH. So, this is F plus 5 will be F plus 1 is 10 14 and this is 15, this is 838. So, I want to transfer the data from, this is the starting address and ending address will be 3854. So, that the memory has to be increment after each transfer. So, this will be now auto increment means 0. Then I want to transfer a block of data. So, 10 because I want to transfer 1 kilobyte. So, this will be block of data. So, this is 10. So, the corresponding this one is 8, this one is 7. 87H we have to load onto the mode register whose address is, the address of the mode register is here, this one 0BH, this is mode register. So, move AL comma 87H out, 0BH is the address of mode register comma AL. This is for the initialization. Then I have to load this count. What is the count that I want to load? 1 kilobyte using channel 3. So, what is the address of channel 3 which holds the memory starting address? Again coming for the table. So, I want to store the starting address in channel 3. This is channel 3 memory address, this I have to load with 03FFH and this is count register is 1K, sorry, this is 03FFH because count, and the starting address is, you have to load here. What is the starting address I have taken is 3455H. You have to load here 3455H. So, the address of channel 3 MAR will be 06H and count register will be 07H. So, I have to use these addresses 06 and 07. So, 06H is memory address register and 07H is count register for channel 3. These are the address of channel 3. So, first you send the lower order address onto this memory address register. This is a 16-bit register. So, the address is 3455H. The starting address is 3455H. So, the previous two instructions I have written here, which are move AL comma 8408, move AL comma 84, I will write here for the complete nets of this program, move AL comma 84H08 out 08H comma AL. Then move AL comma, what is the lower order byte of the starting address? 3455. So, 3455H, this is lower order byte. So, you take that lower order byte onto AL out. So, what is the address of this MAR is 06H, out 06H comma AL. This is possible actually to transfer the entire 16 bit also onto 16 bit port. Okay. Here I am assuming only 8 bit addresses. Then move, you take the higher order which is 34H onto same memory address register whose address is 06H comma AL. These 4 instructions will load memory address register of channel 3 with 3455H. Then you have to load the number of bytes to be transferred. Okay. So, the number of bytes is 1 kilobyte, and what is the address of that count register is 07H. Again you take move AL comma for 03FF, 03FF is 1 kilobyte is 03FF. The lower order address will be FF, higher order will be 03. You take the lower order FFH out. The address of the count register is 07 for channel 3. So, 07H comma AL, move AL comma 03H out onto 07. So, this will load the count register of channel 3 with 1 key 03FF. So, we have given all the specifications. I know the starting address, I know the number of bytes to be transferred. Then you have to enable the DMA. So, here in the previous this command word, here we have disabled the DMA. So, by disabling the DMA only you got this one. So, here we have disabled the DMA by putting 1 on the corresponding pin. Now, I have to enable for the data transfer. So, what will be this? If I enable this, this will become 80H. So, move AL comma 80H out 08H comma AL. This 08H is the address of command register. So, I have now enabled the DMA. DMA will be enabled. Then the 1 kilobytes will be transferred. After that, the terminal count will be reached, it will stop the process. This is about the programming of 8237. So, the important task here is, first you have to decide command word register using this format. So, you have to select, these are the specifications. So, it depends upon these specifications, you have to find out what is the corresponding data to be loaded into command word register. Then based on these specifications, you have to decide what data has to be loaded into mode register, and so you have to first of all interface the 8237 to microprocessor to generate the address of mode register as well as command register. Then you take the corresponding data and you load onto the corresponding addresses. Then the next step is you have to load the starting address of the memory in the selected channel, and then the count onto the channel. Then you enable the DMA. So, this is how we can program the DMA. Now, corresponding to this two modes, slave and master mode, we can operate this in master mode as well as slave mode. (8237) modes. In master mode, I have discussed the 7 or 8 steps in the earlier lecture. So, the step by step procedure that follows to operate this 8237 in master mode. In slave mode, simply, so this DMA controller will be acts as a slave mode. So, in that case, simply this 8086 will be connected to memory, address bus, data bus, control bus. and this is DMA controller 8237. This will be DMA hold request, hold acknowledge, and here we will be having IO peripheral or IO such as hard disk. This will be connected to the address and control bus of this one, and this will be DMA request, this will be DMA acknowledge. This is DMA request, DMA acknowledge, and this is hold request, and this is hold acknowledge. This is the connection diagram in case of slave mode. In case of master mode, we will be having switches here, switches in case of master mode. This is about the different modes of 8237. Now coming for the final the connections between the microprocessor and 8237. The other side I am not showing because their peripheral will be connected. This is 8237. So I am calling as 8237 only, but this can be 8237A also. Okay. This will be having only 8-bit address bus. These are two latches, and this is your 8086. So we know that 8086 having multiplexed address data buses. So I am considering only the 16 address lines. This is latch, this will be having two signals, one is called latch enable signal and output enable signal. This will available as active low signal, and this is latch enable active high signal. This is LE, latch enable. This if I consider this AD7 to AD0, the lower order 8 bits of the address. This is multiplexed bus, this is octal latch. This will have 8 D flip flops inside this. This will be connected to address latch enable, address latch enable. So the output will be here address bus A7 to A0, and this will be now connected as data bus D7 to D0. This is how we can demultiplex the address and data buses. So this has to be connected to the address bus of corresponding address bus of 8237. This is address bus, this is DB7 to DB0. And this output enable bar, this will be connected through address enable line of 8237. Now coming for the higher order 8 bits, there will be another latch. So this also will be having latch enable, and output enable. Output enable is normally active low signal. So this will be address latch enable will be connected, but this will be connected through NOT gate. If this is enabled, this will be disabled. If this is enabled, this will be disabled, because AEN signal is connected through NOT gate, and this LE, latch enable signal, will be generated by now address stop. So in case of lower order address, latch enable will be generated by the ALE signal, whereas in case of higher order address bus, so this input will be now AD 15 to AD naught. Here this output will be A15 to A naught. So, this and this together will act as 16-bit address, because we have the memory address is 16-bit, the starting address of the memory MAR is 16-bit. So, we have to place 16-bit address onto this bus. So, this is how we can use this address stop signal and AEN signal to demultiplexer address and data buses. So, this address stop is basically used for demultiplexing the higher order bus, and AEN is of course required for both the buses, and the lower order bus will be demultiplexed by using AE, address latch enable. The remaining signals are directly connected, ready to ready, reset to reset. These are ready, this is reset. This is ready. And similarly we have memory read bar, memory write bar, IO read bar, IO write bar. Memory read bar, memory write bar, IO read bar, IO write bar. But here we have only M by IO bar, read bar, write bar. Using these three signals, using some circuitry, this we have discussed in the earlier classes, some logic circuit, we can generate 4 signals: memory read bar, memory write bar, IO read bar, IO write bar. So, these are correspondingly connected to the corresponding signals. Memory write bar, IO read bar, IO write bar. This is about the connections between 8237 to 8086. So, these are all the complete details of the DMA controller 8237. Thank you.